Good morning, everyone, and thank you for joining me today. My name is Mustafa Masood Ahmad, and I'm excited to present my operational research assignment number 1. Today, we will be diving into the fascinating world of graphical method, linear programming problems, and focusing on the daily production mix conundrum at Alemco. Now, let's dive into this problem. Imagine this: Lemco manufactures aluminum sheets and aluminum bars. The maximum production capacity is estimated at either 800 sheets or 600 bars per day. The maximum daily demand is 550 sheets and 560 bars. The profit per ton is $40 per sheet and $35 per bar. Determine the optimal daily production mix. In this problem, the industry faces a strategic puzzle every day. With a maximum production capacity of 800 sheets or 600 bars per day and a fluctuating demand of 550 sheets and 560 bars, the company must navigate a delicate balance between supply and demand. Adding to the complexity, the profit margins vary, with $40 per ton for sheets and $35 per ton for bars. The challenge is clear. How can Alemco determine the optimal daily production mix profit while meeting its demand? Let's break down the problem into its core components. What is the problem? Alemco, a manufacturer of aluminum sheets and bars, faces the challenge of determining the optimal daily production mix to maximize profit while meeting demand. Who has the problem? Alemco, a leading manufacturer in the aluminum industry, encounters this production optimization challenge. Why should we solve this problem? Maximizing profit while meeting demand ensures efficient resource allocation and customer satisfaction. How will I know this problem has been solved? The solution will maximize profit while meeting maximum daily demand and production capacity constraints. Now let's dive into the answer. To begin with, we define our decision variables x. X represents the number of sheets produced, while y denotes the number of bars. With this in mind, we construct our profit function as 40x plus 35y. Constraints come into play as well. X is less than equals to 550 and y is less than equals to 560. As you can see, these constraints were given here, that the daily maximum demand is 550 sheets and 560 bars. These constraints reflect the maximum daily demand and production capacity limitations. Now we are given that the maximum production capacity is estimated at either 800 sheets or 600 bars per day, so the equation becomes 600 divided by 800x plus y is greater than equals to 600. Now this 600 divided by 800 is the proportion of bed and sheet, so that we can meet the demand required. For 600 it means for bars, and for 800 it means for sheets. Now let's dive into its solution on the graph. Let's visualize our solution. On the graph, we plot the inequalities representing our constraints. This graphical presentation allows us to identify the feasible region where all constraints are satisfied. Within this region, we pinpoint critical points such as 53.33, 560, 320, 560, 550, 387.5 and 550, 187.5. Now these coordinates are found out by the inequalities and equations above. We plotted down these constraints and these equations on the graph and concluded these coordinates. Now, with our graphical representation in hand, let's move on to profit calculation. By evaluating the profit function at each corner point of the feasible region, we identify the maximum profit. We take all of these points A, B, C, D and calculate their profit function, which was 40x plus 35y, and put in the values of x and y into the profit function. Any vertex, any function giving the highest profit will be considered as demand required for optimal daily production. Now let's see, at point A the profit was 21,733, while at point B it was 32,400. At point C it was 35,562.5. At point D it was 28,562.5. So the highest profit among these equations, these vertices, are point C. Remarkably, the optimal production mix yielding the highest profit is found to be 500 sheets and 387.5 bars. Now, based on our Alemco's maximum production company capacity and the maximum daily demand, the company should produce 550 sheets and 560 bars to meet the demand and maximize profit. If there are constraints and a full demand cannot be met, the company should prioritize the sheet production because it earns more profit. The concept of economics of scale is not applicable here as full production is possible. Now let's explain this solution to you. The optimal daily production mix for Alemco can be determined using the data on maximum production capacity and maximum daily demand. Given the company's maximum production capacity, it can only make either 800 sheets or 600 bars per day. However, the maximum daily demand is 550 sheets and 560 bars, which is less than the production capacity. Therefore, Alemco should produce 550 sheets and 560 bars to meet the demand, which maximizes its profit. It is important to note that profit per ton is higher for sheets than for bars. If there is a scenario where Alemco cannot meet the full demand for both products due to constraint, it should prioritize sheet production as it gives more profit. Thank you so much. This was it, and I hope you like my presentation. This is Mustafa Masood of class BSE 3B signing off.